thank you, Dr. Dai, for doing this presentation. This one took a while for us to organize because we had extra hoops to jump through. And thank you for everybody who came here. I just wanted to say a few words about MIRA because I think, I mean, many of us, at least in Europe and the US, have heard of MIRA by now. We've been talking about it for a couple of years, but we haven't reached into Asia very well. And so I wanted to say a few words about what MIRA is to the folks who may not be familiar with it. So MIRA is just an international working group, and the purpose is to get modelers, in situ folks, and remote sensing folks together to kind of share information about our separate disciplines and to kind of break down some of the barriers that might be between our disciplines, and so that we can all do a better job at what we do. But we want to do more than just break down the barriers between disciplines. We also want to break down barriers between time zones, countries, and institutions. Just make it easier for us to all work together. And of course, we want to bridge gender and age barriers. We want to enable senior scientists and junior scientists to work next to each other and give junior scientists more access to the senior folks. So the way we have done this so far is we have these focused interdisciplinary topics, which I don't want to go through them right now because I don't want to spend a whole lot of time on this, but if you are interested, you can go to this webpage here and see what the topics are. We also hold bi-monthly webinars like this, and we rotate the time zones in an effort to be able to reach everybody. And then we record them as well, like Eleni says, so that way, if it's at an uncomfortable time for you, you can still get access to some of the information on these webinars. We have newsletters that are supposed to be quarterly, but they aren't always. We also host MIRA sessions at major conferences like AGU and Apollo. And starting in 2025, we will also have a workshop, and that's going to be in Athens. Many of you on this call are from Athens. I had the opportunity to go there for the first time last year, and it's a really wonderful place. So I think if you get an opportunity to go to Athens this summer, that you should take us up on this. And the last thing I wanted to say is that, you know, right now we've got about 30 countries, and we're still trying to grow. And this is an open international working group. Everybody's invited. Anyone can join our news list, which is right here. And if you join that news list, you'll get updates on things like this this workshop and other activities that we're doing. And with that, I will stop sharing so that Eleni can take over again.
Thank you very much, Greg.
I'll be happy to answer any questions as well.
So are there any questions? I would like to thank very much, Greg. We are also very excited to host this seminar along with MIRA. So now and we are also very excited about today's webinar. In this webinar, we have Dr. Guangyao Dai. He's an associate professor at the Faculty of Information Science and Engineering in Ocean University of China. His research focused on multi-platform atmospheric and oceanic LiDAR developments, including spaceborne, shipborne, and ground-based systems. And he also uses these measurements on scientific applications. Today, he will give us a talk about the aerosol and carbon detection LiDAR on board the DQ-1 atmospheric environmental satellite. And the ACDL LiDAR provides globally vertical distributions of aerosol cloud optical properties with high vertical resolution since 2022. And we are very excited to hear about the news about these measurements. So with this, I will start sharing the screen.
Yes, thank you. So good morning, good evening, and good afternoon, everybody. So I'm sorry, firstly, I apologize for the time delay for my presentation. And it's my great honor to give this talk to you regarding the calibration, the quality control, the retrieval, and the application of the ACDL measurements. And The next slide, please. This is the content of this talk, including 6 sessions, including the ACDL mission and the requirements, and also the second one is the ACDL system principle and the development. The third one is the ACDL on-orbit performance, and the fourth one is the aerosol and the cloud optical properties, which this is also the main body of this talk. And the fifth one is the measurement cases and some applications by using the ACDL data products. And finally, I would like to summarize my presentation. So next slide. For the ACDL mission, and if we look at the sixth report of IPCC in 2021, and we can find the CO2 and the methane are the main greenhouse gases which are responsible for the global warming. And we can also see from the figures that they contribute a lot for the global atmospheric warming. It's about 1.3 degrees. And if we look at the second one, we can also find that the aerosol and cloud also plays an important role for the global climate change. So next one. This is why we have to do some measurement about this CO2 and the aerosol. Actually, at this moment, we have several instruments or techniques which can be used for the measurement of the CO2, including the passive instrument and also the active instrument. And for the passive instrument, the value is the grating spectrometers for the FTF. And for the active instruments, we developed the space-borne lidars based on the IPDA techniques. But if we look at the disadvantage and the advantage, and we can find for the active instrument can provide the daytime and nighttime for the CO2 measurement, and it can provide a very high measurement accuracy with a very small footprint from the satellite, and it can also find some higher probability of cloud-free and make it possible for the globally profiling of the CO2 distribution. So I would like to say the space-borne lidars has the most potential for 1 ppm accuracy of CO2 concentrations over nights and days. Okay. So for the aerosol measurements from all about the world, actually we developed several missions from the satellite. The well-known Calypso, which was retired, and it provides us a lot of information and knowledge about the globally distributed aerosol. And finally, we get the Euler's Aladdin, and it can also give us the modified and also the aerosol informations. And now we got the ACDL and the athlete measurement at different wavelengths. And in the future, we can also see some plans, mission plans about the US from the US, our colleagues from the US. And I would also like to say that probably the high-spectral-resolution Lidar techniques is the preferred method for the profiling of the accurate aerosol measurement from the satellite. Yes. In this slide, I would like to say something about the DQ-1 satellite. The satellite is operated at the orbit height about 700 kilometers with an incline angle about 99 degrees. And the ascending time of the local time is about 1:30 p.m. There are 5 payloads. In this satellite, and the main payload is the ACDL, which can provide the measurement of the CO2 and the aerosol cloud profiles at the meantime. And by using these 5 payloads from the satellite, they are used for monitoring the aerosol and the air pollutions all over the world. Yes. For the second part, we would like to show you some ACDL system principle and development. The left fingers present you the optical layout of the ACDL. You can see the lasers, the telescope, and also the different channels for the CO2 and for aerosol measurement. And actually, it is a hybrid measurement method in this one LiDAR system, including the IPDA method used for the CO2 measurement, and also the high spectral polarization and the double wavelength measurement used for the aerosol and cloud profiling. If you look at the right one, you can find the double pulse on and off lines measurement for the differential absorption measurement of the CO2. And we used the iodine filters for the measurement of the for the measurement of the aerosol. Yes, next one. In this tables, I give you some specifications about this LiDAR, and including the wavelengths. We have 3 wavelengths: 532, 1064, and 1572 nanometers. And the laser energy is pretty high. It's 130 and 190, and higher than 40 millijoules. And what I would like to say is that the PRF actually is 20 hertz. But as I mentioned above, it is a dual pulse of configuration, which means actually it is 40 hertz for the emission. And the telescope aperture is about 1 meters, and it provides some 5 receiver channels, including the 532 nanometers high spectral resolution channel, and the 532 parallel and crossed parallel polarization polarized channels, and also the 1064 nanometers for the aerosol measurement, and of course the CO2 measurement channel. Yes. In this slide, I present you some formulas for the retrieval of the CO2, and including the Lidar equations, the DAOD calculations, and also the weighting functions, which is essential for the retrieval of the CO2 concentration. And I will not try to describe this very well, because I'm not mainly working on this. So the next slide. Using this slide, actually, we have 3 channels signal processing, including the molecular channels, perpendicular, and the parallel channels. If we use this 3 channels from this 3 channel signal, we can calculate the backscatter coefficient, the extinction coefficient, and finally we got the Lidar ratios. But if we look at the 2 wavelengths, we can also calculate the color ratios from different measurement from these 2 wavelengths. Yes. Okay. By using this LiDARs, we can get some data products. Actually, we used different levels from the international regulation, actually. But what we use now is the level 2A, the attenuated backscatter coefficient with the systematic consistent correction. But actually, we are still developing the calibration constant. So if we look into the L2A, we still try to get back the calibration constant and try to calculate it again. And then we can get the L2C, the level 2C data products about the cloud and aerosol products, including the extinction coefficient, the backscatter, the depolarization ratio, the AOD, the Lidar ratio, and even the color ratio. Yes. Actually, this satellite was successfully launched from Taiyuan Satellite Center at 2:16 AM on April 16, 2022. And next slide. And actually, from May 20th, 2022, it's already continuously operating about more than 2 years. Actually, it's almost 3 years, and the laser fires about 1.82 billion double pulse. And if we look at the left fingers, we can find that the total laser energy decrease very slowly with only about 8 million joules per year. But if we look at the right one, we can find that the laser energy drop rate of the 1572 nanometers is pretty large. And this is why we adjust the laser amplifier and to increase the 1572 nanometers pulse energy on October 7th, 2023. And we can find the energy of this this wavelength is up to 45 million joules. Yes. Actually, if we use the absorption differential absorption and high spectral resolution, we have to use the very stable frequency or the line width for the lasers. This is why we keep an eye on the monitoring of the frequency stability of the different wavelengths. But this is, for example, for the 1572 nanometers, we can find that the standard deviations, the RMS is about 0.4 megahertz. And if we try to calculate the island deviations, it is found that it is less than 30 kilohertz at 10,000 seconds. So this is pretty nice performance on the orbit. And this is also give our great confidential to do some calculation and the retrieval of the CO2 and the aerosol optical products. Yeah. So let's move to the next session. Is the aerosol and cloud optical properties. And the ACDL applied the high spectral resolution Lidar with an iodine vapor absorption filters. This iodine works at the 1110 lines with the bandwidth is smaller than 2 gigahertz, and it is also equipped with the detection of the polarization. And we focus on the 532 nanometers for the cross and the parallel polarized channels and the high spectral resolution channel, and we also keep an eye on the calculation of the 1064 nanometers channel. And the specifications I have presented you before, and this is I will not do it again. So this is the
sorry.
no problem. Yeah. For the ACDL aerosol and cloud data production, it is pretty long, and actually the right side finger you can find the flow chart of this of the very brief description for this production, including the data preparation and also the pre-processing and also the optical properties retrieval. And actually, in this work, we developed a data processing and optical properties retrieval method, which is adopted to the specific characteristics of the ACDL for the global observation. And at this moment, we are developing, organizing the spaceborne high spectral resolution Lidar aerosol and cloud immersion algorithm ATBD. But unfortunately, it is in Chinese. Let's see if it's possible, we can translate it to English ones. And up to now, we have formed three versions for the retrieval, and at this moment we're using the baseline 03, and baseline 03 has already deployed on the CMA servers, and it is working automatically, and it will produce some optical properties. Yes, and for some very detailed information, you can try to get some information from this manuscript. Yes, next one. During the data preparation section, the first thing we need to do is the pulse splitting. Just as I mentioned before, we have the configuration of the on and off lines for the measurement of CO2. This is why the AULUS measurement follow this same configuration. So this is why we also use the double pulse for the measurement of the AULUS for the aerosol. And we can find that the laser, the first pulse, we call it old pulse, is launched 200 milliseconds before the second pulse. The second pulse, we call it even pulse. And after a delay time, the delay time we call it time delay aerosol, and the ACDL reserve subsystem starts to collect the backscatter lines. And here I also provide the original vertical resolutions. Vertical resolution about 3 meters and 24 meters. But for the for the final data products, the vertical resolution is about 50 meters. Yes, next one. Another part of for the data preparation is the background noise extraction. We try to give you a demo for the nighttime and daytime. For the nighttime, we try to get the background noise at different channels, including the parallel one, the perpendicular one, the molecular ones, and also the 1064 channels. And if we look at this, the values, we can find the nighttime background noise is pretty low. It's smaller than 0.05 volts. But if we look at the daytime measurement, we can find it varies from different terrains. For example, if it hits the ground and if it hits the ocean, we have different behaviors of the background noisy. And this is why we have to try to calculate the background noisy profile by profile. And this is very important for the data preparing. Yes, next one. Actually, for the background noisy, we did some statistical analysis about the nighttime and daytime. And for the nighttime, we did some background noisy statistical things. We can find that it keeps increasing from the South Pole to the North Pole, and this is because the satellite is moving from night to the daytime. So the background noise is keep increasing. For the daytime, we also try to figure out the background noisy characteristics, and we can find some the shape is like M, but it depends on the terrain and also depends on the elevation of the sun. Yes. So after this data preparing, we move to the next step about the pre-processing. Actually, in this pre-processing, the most important thing is that we have to do the calibration things. And we can also, at the right side, I also provide you some things about baseline 04 and baseline 03 and the baseline 02. The difference is that we use the different calibration constant at different part and different with a solution of one multiple 1 degree. And the next one, please. Okay, so the ACD apply for the calibration procedure, we used the ACD applied the molecular normalization techniques as the theoretical foundation for the calibration. But it is not possible to monitoring the background noise. This is why we selected the 21 to 25 kilometers as the calibration region. The reason for why we choose this why we choose this region is that it is high enough to get to the relative free of the aerosol, but it is low enough to ensure the background noise. We can get the useful and the valuable backscatter signals from this part. And there are three formula from the different channels. We use this formula to calculate the calibration constant for the different channels. The first one is the parallel polarized channels, and the second one we used the PGR, the gain ratio, to get the cross polarized channels. And the third one is this formula to get the high spectral resolution channels calibration coefficient. And the right part, we provide you some obvious measurement of the calibration constant, and you can also find some information about the calibration constant and method in this manuscript in the EMTD. Yes. So after this calibration, finally we got the power signal for different signals for different channels. Here in this slide, I present you some the parallel cross molecular and 1064 nanometers channels. We can find that they are it is pretty good. But if we look at the molecular channels, we can find that the aerosol and the very thin cloud, the crosstalk from them is blocked pretty nice, and it is very clear. Yeah. So after the processing, we got the the power signal, and then we move to the next part of the optical property retrieval. And the first things for this retrieval part is the sub-channel denoising algorithm. Because you can see the left upper one, and because we have four channels, the four channels has different behaviors. So we used different denoising algorithm for different channel. So for example, for the molecular channel, we used the median filter. We use the sliding window, and we also using some wavelength domain denoising and some other method to do this denoising things. And after denoising, the next step we have to do is the cloud and aerosol classification by using this the attenuate scattering ratio and also some geometry information. We try to get separate the cloud and aerosol things, and we finish the feature detecting. And the next step is we would like to do some aerosol classification. But when we got the feature detection, we move to the next step. Next step is the optical properties retrieval, including the aerosol backscatter coefficient, the extinction coefficient, the depolarization ratio, the Lidar ratio, and also the color ratio. And if we look at the data products from the baseline 03, we got the products is for one orbit is about 1.1 gigabytes. So it is pretty large. It is pretty large, and we are also thinking about the transfer and also the data sharing with our colleagues in Europe, because what we want to do in the future is we would like to share the ACDL data to our Dragon 6 team, including the Tropos, including our NOAA and also some other interested colleagues. Yes, next one. So from this one slides, I want to show you just one example of the total depolarization ratio here. And for the left things, the left one is the nighttime measurement, and the right one is the daytime measurement. For the nighttime measurement, the ACDL travel across the Europe and also the South Africa until to the ocean. And from this measurement, we can find the depolarization ratios of different aerosols and cirrus cloud. And if we look at the daytime measurement, we can find that it's also pretty good and pretty good measurement here, and without too much noisy. Yes. The next one is the backscatter coefficient. From this, because the backscatter coefficient is the most very early data products from this ACDL. If we look at this one, we can find this the same nighttime and daytime orbit measurement here. But from the backscatter coefficient, we can see the stratospheric aerosols. For example, it is somehow sulfate. It is from the Tonga volcano erupted. But we mentioned we measured this case is just 5 months later after the eruption, and this is pretty amazing. And we are still keep an eye on this. But the next slide. Next slide present you the extinction coefficient. You cannot see the sulfate anymore. This is probably because we need a longer time integration or some other things. We are still working on this. But if we look at the regular measurement of the extinction, it is still very nice. And by using the extinction and the backscatter, and then we got the Lidar ratio. The Lidar ratio, we can also here we can see the dust measurement and also some other measurements there. And this is also interesting. We can also get the Lidar ratios at nighttime and daytime. Yes. So this is attenuate color ratio. We call it attenuate color ratio because we are the calibration for the 1064 is still needed, and but if we look at the nighttime cirrus color ratio, it is higher than 1. So this is also we need to do in the future to fix this problem. It is, and we are still working on these things. Yes. So if we got this vertical distributions of the optical properties from this of the extinction, and we can calculate the layered AOD. Actually, the layered AOD we call it if we and it is I would like to say if we look at the different layers AOD, we can notice the vertical distributions of aerosol, and we can find out the vertical range of the aerosol loaded. Yes, and this is also an interesting measurement. Yes. And after the optical retrieval, the next things for us is to do the validations. And for the validations of the ACDL measurement, we try to figure out several measurements from the ground-based and also the satellite measurement. The first slide I give you is the ground-based Raman Lidar and the high-spectral resolution Lidar. And in this slide, the Lidar is located at Zhangye and Dunhuang in China. We use these two lidars for the measurement to compare the attenuated backscatter from the ground-based lidar and the ACDL. And if we look at the profile, we can find that it fits very well. And next slide. And we also try to compare the simultaneous measurement from the ACDL with the MPL net. We find 3 locations and 3 sites from the MPL, and we compare the polarization ratio and the backscatter coefficient, and we can find that they are also pretty nice. And we also calculate the relevant error, the relative errors from these 2 optical properties. We can find that the errors from these 2 measurements is small. Most of them are smaller than 20%. Yes. The next one is that we use the measurement from the sun photometer. The next one, please. Yes. And we also compared our measurement of the ACDL using the sun photometer measurement. We also get the data from the AeroNet. By using all of the AeroNet set which is available for the comparison, we can find that the RMSE for the comparison is equal to 0.12. But I will not say that is the perfect comparison, but I would like to say it is a pretty good comparison. And with the R square is about 0.8, 0.8. But if we the comparisons we compare the simultaneous measurement, and but if we look at some certain regions, for example, if we focus on the Asian size, just as the right figure shows, you can see that the mean bias of the AOD comparison is less than 0.05. And if you look at the comparison over the ocean, which means it is a single aerosol type, we can also get a very good, better validation things from there. But I would like to say that we're still working on this. We're still working on this because we're still trying to integrate, upgrade the calibration constant. We try to do the much more accurate measurement for the AOD. Yes. So after the ground-based measurement, we also look up to the space-bound lidars, and we also try to find some simultaneous and co-located measurement from the capsule. And we find one measurement from 6 June 2022, and we also present you here the attenuated backscatter from the DQ-1 and the Calypso. And we can find the signals from these 2 lidars also feels very nice. And but I have to say the Calypso energy is dropping, and but it can still provide us a very nice benchmark for the comparison. And this is also give us a lot of confidence to do this further research. And after this, and we also compare the depolarization ratio, the attending the backscatter, the extinction, and even the lidar ratio from these 2 lidars, and we can still got very nice comparisons from these 2 lidars. Yes, next one, please. So yes, of course, we in the future, just a few days ago, we also joined the Carval, the workshop for the Earth-Care. And we are also very excited to see the release of the Earth-Care data. And what we will do, and what we surely will do, is that we want to compare the measurement from the ACDL and the DQ-1 measurement. And actually, actually, this is animation. I think the right one. Could you please try, Eleni? No, sorry. Actually, it is no, it is animation. Yeah. Okay, so okay, it doesn't work. Yes. Okay, okay. So if the thing is if we look at the obvious prediction of the ACDL and the Earth-scalar, and we can find that they are still very high probability to meet each other. And what we want to do is that we want to compare the optical properties from these two ACDL to Lidar. But the most important thing is that these two Lidars works at different wavelengths. And the first thing is we want to do is that we have to finish the wavelength transfer. Also, we should pay attention to the angstrom exponent. And if I remember correctly, the Earth-scalar is releasing data publicly from maybe 13th January of this year. And actually, my students, Dr. Conway-Thun, will move to Tropos for the joint research regarding the ACDL and the athlete. And this is also very interesting. And I hope so, because of the visa application is pretty hard for us to travel to Europe. Yes, the next one. So after the validation things, what I also want to show you some things is about the CO2 concentration measurement from all about the world. And the ACDL provides us the unique CO2 measurements on daytime and nighttime, and we can also see the pretty high latitude in the near the South Pole and the North Pole. This is pretty nice, and in the Arctic and anti-Arctic measurement by using the active measurement, which helps to get more data for the passive measurement. Yes, next one. And not only using the data from the ground echo, we also use the cloud echo signals, and which can help us to increase the global coverage of the ACDL measurement. Yes. So let's move to the next session. Is the application of this ACDL data. And by using the depolarization ratio, the Lidar ratio, and the color ratio of the ACDL, we try to classify six different kind of aerosols, including the mixed dust, the mineral dust, marine aerosol, polluted air, marine pollution, and the smoke. This is I present you some one demo, and the next one. And by using this classification, we try to track one Canada wildfire on 5th June 2023, and we can also find the depolarization ratio and the Lidar ratio because of the wildfire. And this is also a nice measurement. Yes. Okay, I like this. I like this figure. Actually, this is also one animation, I think, but it doesn't work. I'm sorry. Does it work? No. Actually, we use this is one day's measurement for the ACDL. We try to use this one day's measurement from the ACDL. We want to do the 3D profiling of the PFC measurement on the 21st July 2022. And this is actually very interesting thing. Actually it is animation because we can see the 3D constructor of this PFC. This is very interesting. But if you look at the purple lines about the okay.
Okay, no, I was hoping, but no, it's not working.
Okay, so
okay,
we stop. So, but if we look at the purple lines about the PFC, and we can see the ozone mass mixing ratio, and what we are doing is what we are doing now is we are trying to find out the correlations between the optical properties and also the ozone missing concentration. We think this is also a very interesting topic for this research. Yes, the next one is for the PM 2.5, I think. Yeah, if I remember correctly. Yeah. So the PM 2.5 measurement, we also use the ACDL measurement, and also we also use the meteorological data from the ERA file. We can find the PM 2.5 distribution over China, and with open file or multiple open file degrees measurement. Yeah, this is also what we need to do for the Chinese government. Yes. And in the future, we would like to use the ACDL data into the research field regarding the meteorology and the NWP. And what we are doing, what we are doing is that we used the atmospheric inputs from the ACDL to do some simulation about the spaceborne wind lidars simulation system. The simulation used the coherent LiDAR and the incoherent LiDAR together, and we by using the ACDL inputs, the aerosol, backscatter, and cohesion and extinction things, and we can calculate some information about the model, and finally we got the different parameters for the model spaceborne with LiDAR. It also helps a lot. And what we want, and we will use the ACDL for the further research. And actually, this work is already somehow partly finished. And if we have another opportunity, I will introduce these things to you and in another talk. Yes. So let's move to the last slide. I would like to summarize my talk here. The first thing is that the ACDL is operating with both IPDA and the HSRL subsystem in one space lidars for the first time. And after the successful launch, the ACDL has been operated almost 3 years now, and we can see the space laser is working very, very well, and the frequency stability is amazing. And we also get we also use the ACDL data to get the optical properties, and we use the optical properties and to measurements, and the ACDL data can be used for the research on the PFC, the PM 2.5, the aerosol classification, and yes, of course, we also use the ACDL data for the retrieval of the visibility and for the vertical, horizontal, and slant visibility. And we also want to use these things to the meteorology and the NWP things. And the last one is what I want to say is that the international validation of the data application is also important. But even though the data releasing is on the way, actually just 1 week ago, the user of the satellites tried to contact us to ask for the regulation of the data sharing. This is good things that because they are also thinking about the data, the data releasing. But we cannot with them. This is why we are trying to follow the Earthcare Kawa workshop, and we are trying to do the constructor of the Dragon systems. And we would like to use the Dragon system to release and to share the data with you from Europe, from different institute, and even for the US. We are happy for this. And if you have interested in some data from the ACDL, just tell me the orbits, tell me the time, tell me tell me the zone, tell me the region, and we will try to give you the optical properties as soon as possible. And I also present you my email address, and if you have some further questions, you can email me, and I will try my best to come back to you. Thank you. That's all.
Thank you very much, Guangyao, for this excellent presentation, and we are amazed with these nice statistics. Actually, I think ACDL is the way to continue the long time series from Calypso towards Earth here also. For how long do you think it will be that the Lidar will be able to measure? Do you have a projection now with that you know more about the frequency stability of the laser, the energy, etc.? So the plan is for Earthcare, for example, the plan was to measure for at least 3 years, but now there are ideas for longer.
You mean the lifetime for the ACDL? It is designed is about 8 years. It's pretty long lifetime, yeah, 8 years. But in the first 3 years, it is pretty nice on the performance well, yeah.
So we are looking forward also for some of the measurements. Greg, maybe you would like to comment something?
Yeah, it would be really neat if it lasted as long as Calypso, huh? You also showed some PM 2.5, which I think is another nice application of these type of lidars. And I don't know, have you been able to do any detailed comparisons with what you're getting from the surface measurements with the PM 2.5?
For the PM 2.5, yes, we compare. Actually, we developed one algorithm by using the ACDL and also the ERA5. Yes, of course, we compare the PM 2.5 with the surface measurement, and we have to find out the relationship between the AOD and the PM 2.5, and we also try, and we have to use the simultaneous measurement from the surface. Yes.
Right.
It's like a training, a test, and a validation.
Right.
Something like this.
Yeah.
Yes.
Well, the images are very nice after looking at years of Calypso data. I mean, you showed it nicely how clear your images are, and the Calypso data are kind of grainy. They're grainier now. Well, I should say now, but the recent ones were more grainy than years ago, but they were still grainy years ago. So this is a big improvement. I really appreciate what y'all are doing.
We are very excited when we also would like to use measurements collocated with our Pangea observatory measurements here, which is a remote site, and also with Earthcare also, in order to bridge with Earthcare and Calypso, what Greg mentioned to evaluate the lidar ratio of Calypso now with these HSRL measurements and be able to build a long time record between Earthcare, Calypso, and DQ-1 now. So it is. We are looking forward for the measurements and how this can work. I think that because you mentioned about the size of the data, an idea would be if the data can be cropped in the regions that the different teams will be needing. So, for example, I don't need whole track. Maybe we need the collocations between the satellites and above the sites. This would be a way forward.
Yes.
Because this is the same as the problem with Earthcare.
Yes. Maybe I'll find the solution for the transfer of data. Yeah.
Also, you saw these elevated layers in the stratosphere, and we also, from the first measurements of Earthcare, we saw these measurements. Now, Aerosol also had these stratospheric layers, observations of these layers, and Calypso. So now we have in the stratosphere a lot of measurements to understand better what is going on there. It is much more live than what we originally believed, or what was the case in previous years.